Alright, so let's discuss some state space basics. I just want to go over the reasons that we want to use state space. Alright, the first and most important reason to use state space over a transfer function representation is that it allows us to represent any dynamic system. And that system could be linear or nonlinear, could be time varying or time invariant, or it could be continuous or discrete time. Another reason is that we can easily extend state space representation to multiple inputs and multiple outputs. Of course, in an undergraduate controls course, this isn't all that important, but it's still useful to see the representation. All right. In addition, it's very easy to implement algorithmic procedures, and in particular, if you're working with discrete time systems, you might be taking just discrete steps. So that's very useful. All right. Just want to highlight again the form. All right, the form is that we have x dot is equal to ax plus br, and this is the state equation where we have x dot, which is a differential quantity, which is n by 1, and then an A matrix, which is n by n, where n is the system order or the number of states. And then, of course, x has the same dimension as x dot. It's just the non-differential version of x dot, of course. B is a matrix which is size n by m, where m is a number of inputs. All right, and then R, which is my input, is m by 1. All right, and then we have the output equation where y is equal to cx plus dr. The number of outputs is equal to q, and so y is q by 1, making c q by n and d q by m. All right, then the last little basic thing about this is the state solution. In the time domain, the solution to x of t is equal to the matrix exponential e to the at x of 0, that's the initial condition, plus the integral from 0 to t of e to the a t minus tau times b r to the r of tau d tau. Now the matrix exponential is a little tricky. It's not just simply taking exp of at. It is actually the sum, which goes for identity plus at plus a squared t squared over 2 factorial plus, and that kind of continues on forever. So the easy way to find this is to actually find the state transition matrix big phi of s, which is the Laplace transform of the matrix exponential, which is equal to the inverse of Si minus A, remembering that I is just the identity matrix, and that I should be n by n. All right. Another thing that's important to note, and that helps us relate to this to transfer functions, is that the determinant of Si minus A inverse is equal to the characteristic equation, which is the same as the denominator of the transfer function.